Hey guys, welcome back. So in this video I wanted to kind of prove the max height and range equations and then also show you why you have to fire directly at the monkey in the monkey demo. So we're going to start with the max height equation, and basically what we want to do is calculate the time for a projectile to go up and use that and plug it into the delta y equation. And in order to find the time that a projectile takes to go up, we need to make use of the fact that Vy final will be 0. Now Vy initial will come from the triangle, so Vy initial is going to be V initial sine theta. So we can use the velocity equation and say Vy final equals Vy initial plus gt. Again, g is negative 9.8. So Vy final is 0. This is V initial sine theta and plus gt. Now this is the time to go up. Okay, so t up is equal to negative V initial sine theta over g, where again g is negative 9.8, so it gives us a positive time. So now we take this and we plug this into the delta y equation, so that's Vy initial times t, this will be the time to go up, and then plus 1/2 g, and then the time to go up squared. Okay, so we know that Vy initial is V initial sine theta, and then we plug in t up is negative V initial sine theta over g, and then we do 1/2 and we have g, and then we have negative V initial sine of theta over g quantity squared. So we just simplify this, and the left term is negative V initial squared sine of theta quantity squared over g, and this term is 1/2, and then there's a g, and then there's negative V initial squared sine of theta squared, and then g squared. So I'm going to just go ahead and get rid of one of those g's, and if you're taking notes at home you could just cross it out, but I want you to see that we have basically the same term. Oh, and I'm sorry, this should be a positive because we're squaring a negative value, so negative Vi squared turns into positive, or negative Vi quantity squared turns into Vi squared. You get what I mean. Okay, so now we have like terms, and as a matter of fact I can kind of take away this. Okay, maybe connect those and call this over 2g, and that's actually a 1. So hopefully that surgery isn't too disconcerting to you. And so in order to make this like terms everywhere, I just pop on a 2 up here and a 2 here. Okay, so I have minus 2 V initial squared sine squared theta over 2g plus 1 positive V initial squared sine of theta squared over 2g. So delta y, or y max, is negative V initial squared sine of theta squared over 2g. Okay, so a couple things. Number one, we're going to get a positive value for the height, the maximum height, because g is negative. And secondly, we are I lost my train of thought, totally derailed. We're going to have to add in, if we start on a cliff, we're going to have to add in that height. And then the final thought is units. Do the units actually work for this? Well, V initial squared is going to be meters per second quantity squared. Divide that by gravity, meters per second squared, and that should give us units of meters. So you can check that by flipping and multiplying. Okay, so that's the first thing. The second thing, oh, and by the way, you can also find this by solving the forgotten equation. Vy final squared is Vy initial squared plus 2g delta y, and I can just do this directly. This is 0, This is v initial sine theta quantity squared, and plus 2g delta y equals 0. And I don't even have to finish this. You can see that delta y is going to be the exact same thing. So v initial squared sine squared theta over 2g. Okay, so the second part is I want to take a moment to derive the max range equation. So range. And we're going to use basically x equals vx initial times the total time. And remember my caveat for this, you can only use the range equation when delta y is 0. So vx initial is actually v initial cosine of theta, and the time to go up is half of the total time, so I'm going to multiply 2 times negative v initial sine of theta over g. And if you don't believe me, just scroll back up and look for the time to go up. So we're saying that t totes is 2 times the time to go up. And this works because we have a nice even launch, so we have a lot of symmetry. What goes up must come down. And so this is a graph of what the path actually looks like, but then if I do a graph of velocity versus time, I'm going to have, corresponding to v equals 0, I'm going to have equal times because I'll have similar triangles. So hopefully that makes sense. Okay, so I multiply this out and I get negative v initial squared sine theta cosine theta over g, and whoops, drop the 2. It's still there. Okay, and you might recognize, some of you have taken trig, that 2 sine theta cosine theta, so this part, is actually equal to the sine of 2 theta. And so if you like, you can actually write this as negative v initial squared sine of 2 theta all over g. And this is g is negative 9.8 meters per second squared. Okay, so much for that. So there's the range equation. Now how about the monkey problem? Monkey problem is this. We have a tree which is a certain distance away, okay? And in that tree, okay, we've got a monkey sort of hanging out. See the tail? It's obviously a monkey. And we're going to say that we have a gun which is firing a bullet or banana or whatever you want at a position of 0, 0. And what we can do is we can track the position of the bullet, so x bullet and y bullet, and we can track the position of the monkey, x monkey, y monkey. And obviously what we want is, well, if we're given sort of the starting position of the monkey, so x monkey initial and y monkey initial, and the starting position of the bullet is 0, 0, we can see that as the monkey falls down, that the bullet will follow a parabola and those two will intersect, as long as the bullet has enough horizontal speed to reach the monkey before the monkey hits the ground. So basically what we need to do is draw a straight line from the gun to the monkey, and this angle theta, if the height of the tree is going to be y and the distance apart is x, we know that we have to fire at the inverse tangent of y over x. But the proof is what we really want to see. Okay, so we want to write expressions for x final and y final for the monkey and the bullet. Okay, for the monkey it's going to be very easy. Okay, x monkey final is going to be equal to the distance x that the monkey is from the tree. Okay, so sorry about that, just had a cat jump on the computer, so I had to pause. And it turns out that the final x position of the monkey is actually just going to be the position of the tree, which is how far the monkey is away from the gun. Sorry about that. And we know that the x position of the bullet is going to be equal to Vx initial times time, or in other words, v initial cosine theta times t. Okay, so if we want those two to be in the same place at the same time, we have to find when x is equal to v initial cosine theta times t. So once again, we're saying that the x position of the monkey is going to be equal to the x position of the bullet. And we want to do likewise for the y coordinates. Okay, so the y coordinate of the monkey is going to be y initial, which is the height of the tree, plus 1/2 gt squared, where g is negative 9.8. Now if the monkey was throwing himself up into the air or flinging himself downwards, we would have plus vy initial times t, but the monkey doesn't have that. So the final position of the monkey is basically y minus 4.9 t squared. Okay, well, what about for the bullet? What is the final y position of the bullet? Well, the bullet starts on the ground, but it does have an initial velocity upwards, so it has v initial sine theta times t, and then it also has plus 1/2 gt squared. So the final y position of the bullet is going to be v initial sine theta times time, and then this will be minus 4.9 t squared. Okay, so what we want to do is to set the y position of the monkey equal to the y position of the bullet. So we have y minus 4.9 t squared equals v initial sine theta times time minus 4.9 t squared. Okay, now this is the important part. In class, we said that the reason that you have to fire at the monkey directly is because both objects are affected exactly the same by gravity. And this is where we see it in the equation. Both of the y equations have a negative 4.9 t squared. So they cancel out completely. And what we get is that the y position of the monkey, the starting position, is simply equal to v initial sine theta times time. Okay, so now let's look at the two equations we ended up with. So I'm going to highlight those. Okay, and I'm going to rewrite them. We have y is equal to v initial cosine theta times time, and I have x is equal to v initial, sorry about that, that's sine, and x is cosine. And here's where the magic occurs. Divide one side by the other. Times cancel, v initials cancel, and what we get is that the tangent of theta is equal to y over x. And this is what we said must be true from the very beginning. So this is how we can set up the projectile equations and prove that you have to fire directly at the monkey.